Having seen pushdown automaton and its equivalent context-free grammars, let us explore more about context-free grammars. So, context-free grammars precisely capture the class of languages accepted by pushdown automaton. And then we started looking at a couple of properties about context-free grammars. For example, given two languages L1 and L2 for which CFG exists, is L1 intersection L2 a context-free language? Similarly, L1 union L2, L1 star, L1 complement. And towards this end, we had a couple of thoughts on this. Let's explore more about the properties of context-free grammars. And most importantly, there are languages for which no context-free grammars exist. So we wish to know, can we come up with something like a pumping lemma, and using which we can show certain languages are not context-free. Okay. So towards this end, what we will do, we will discuss a couple of things. One is how to simplify a given context-free grammar. The next one, we talk about something called normal forms. And once we get to know these two, from normal forms, we can kind of design, or we can come up with something called a pumping lemma. Very similar to pumping lemma for regular sets, one can come up with pumping lemma for context-free languages as well. And with that, we will show that certain languages are not context-free. Often, when we design a context-free grammar, we may come up with certain rules which may not be reachable, which may not be relevant. So, and there will be some rules which are redundant. So, such things we want to get rid of as part of the simplification. So, as part of simplification, we do the following. The first one is remove epsilon rules, except exception is, suppose the start symbol itself gives you like this, then it should be there because epsilon is part of the language. So S is start symbol. If start symbol itself derives epsilon, that should be preserved because epsilon is part of the language, and all other rules, meaning A imply epsilon, B imply epsilon. If you find A imply epsilon for some non-terminal A, then such rule should be removed. So, but while doing so, we ensure that the language is preserved. The class of language, the input language and the simplified one, they both must be same. So the first one is remove epsilon rules. Then we say remove unit productions. So what are unit productions? Productions of this type. Exactly one non-terminal on the left and exactly one non-terminal on the right. Then remove useless symbols or productions that are not reachable. Not reachable symbols, okay, terminals, and so on. So now if you do this, then we will get a simplified grammar, and whose the language, right, meaning set of strings accepted by this grammar and the given grammar are one and the same. Okay, let's look at one example and appreciate each of this and see how things work when we say remove epsilon rules, how does it work with respect to a specific example? Okay, consider this grammar. Now, as part of remove epsilon rules, we want to remove D imply epsilon, C imply epsilon, B imply epsilon. And in this example, we do not have S imply epsilon, so we need not worry about that part. But when I say B imply epsilon, C imply epsilon, D imply epsilon, we should not simply remove it, because the language accepted by this grammar and the simplified grammar, they both must be same. Okay, so keeping that in mind, one should remove epsilon productions. Let's look at S implies AB 0C. So the alphabet 0 and 1, and the non-terminals are S, A, B, C and D. Okay, so now you see that B imply epsilon is there. So if I want to remove, if you substitute B imply epsilon, you get A 0C. Similarly, C implies epsilon. If you substitute here, we get AB 0. And also see that A implies BC and B implies epsilon, C implies epsilon, which means A implies epsilon. So we get A implies epsilon because of these two, which means when you substitute this, we get B0C. Not just that, now that you know A implies epsilon, B implies epsilon, C implies epsilon, you can substitute all of them or two of them. If you substitute epsilon for all, then we get 0. Or you substitute for AB, then you get 0C. Or you substitute for AC, we get B0. Or you substitute for BC, we get A0. So epsilon is reachable, or empty string is reachable from each of them. And these three we obtain by substituting epsilon for exactly one of them. In this B is missing, in this C is missing, in this A is missing. And in these three we substitute for two of them, and in this we substitute for all three. Now this will ensure that if you substitute A implies epsilon, B implies epsilon, or C implies epsilon, whatever string you will generate on the right, that is precisely captured using this. Okay. Now you have A implies BC and B implies 1. B implies epsilon can be removed, because B implies epsilon, what all strings that it can generate over n union t. N union t, all that is listed here. Fine. So now you see that B implies 1, and on the similar line you can substitute B implies epsilon. If you substitute B implies epsilon, it becomes C. Or you can substitute C implies epsilon, so you get A implies B. Then B implies 1 is allowed. B implies epsilon can be removed, because what all strings that one can generate by substituting B implies epsilon is listed here. Then C implies D, and C implies epsilon is removed, because wherever you substitute C implies epsilon, and the resultant string is generated or listed here. Now D implies epsilon can be removed. This can be removed. C implies epsilon can be removed. B implies epsilon can be removed. Fine. So the idea is the following. As part of remove epsilon rules, leave start symbol. If start symbol says S implies epsilon, that should be preserved because epsilon is part of the language. If you find any other non-terminal generating epsilon, then that should be removed as part of this step. But while doing so, you should ensure that the language accepted by this and the simplified one, they both must be same. So keeping that in mind, supposing you find B implies epsilon, now you may generate a string over n union t by substituting B implies epsilon. So that should be preserved, which is why we get strings of this type. And AB0C is as it is. If you substitute B implies epsilon, then we get this. If you substitute C implies epsilon, then we get this. If you substitute A implies epsilon, then we get this. And if you substitute epsilon for A, B and C, then we get this. If you substitute for two of them, A, B, then we get this. Substitute for AC, we get this. Substitute for BC, we get this. And then A implies BC. If B is empty, then C. If C is empty, then B. B implies 1, C implies D. Now you see that epsilon is removed from the grammar and the language accepted by this and this are one and the same. Fine. Now on this, let's apply the second rule, and which says remove unit productions. So what are unit productions? C implies D, A implies C, and A implies B. And in this there are no unit productions. In this there are no unit productions. In this we find. Okay. Again, when we do this, we should ensure that the language accepted by this and the simplified grammar, the grammar we obtain by removing unit productions, they must be same. Fine. So this says A implies BC and A implies C. A implies C is a unit production. This says A implies B and B implies 1. So we see that A implies B and B implies 1. And this can be replaced by A implies 1. A implies B, B implies 1. So you can replace this and remove A implies B. Okay. Now B implies 1 will remain as it is, and look at C implies D. Now you have A implies C and C implies D, A implies C, C implies D, and we do not have any terminal string, any string over sigma star generated by D. Fine. For example, in this case B implies 1, which is why we substituted 1 for A. But no string belonging to sigma star is generated by D. So which means we can remove A implies C and remove C implies D. Okay. So let's write the simplified grammar. So let's write the simplified one after removing unit productions. We get AB0C, A0C, AB0, B0C, S implies 0, R0C, RB0, or A0. Now when we look at A implies BC is allowed, we remove A implies C and A implies B, but we know A implies B, B implies 1, implies A implies 1, so we ensure that that is written, and we write B implies 1, that's all. So C implies D is removed, A implies C is removed, A implies B is removed. But when we remove A implies B, we check what all terminals that it can reach, those things are captured. But A implies C, C implies D, there is no further production from D, so we remove this. So the first step is to remove epsilon, but when we remove epsilon, we may get unit productions, and even these unit productions has to be removed as part of simplification. Remember, the order is important. For example, if you look at this and apply remove unit production rule first, then we try removing C implies D. However, after applying the first rule that says remove epsilon, we may get some more unit productions. So always apply remove epsilon rule first, followed by remove unit productions. Now on this, apply the third one. Third one says remove useless symbols, useless productions, or from a production you cannot generate a terminal string. Useless symbols, productions, not reachable terminals, okay, and or productions using which no terminal string is generated. So such productions we can remove. Okay, let's look at this. We see a non-terminal C, but we do not have any production starting from C, correct? Which means S implies AB0C is a useless production. C is a useless symbol, and therefore this production is useless. This one is, therefore we get AB0. This is also useless production. Then the second one says S implies 0. This one is useless production. B0 is useful, and A0 is useful. Now when we come over here, we see that C is useless, therefore A implies BC is a useless production. A implies 1 as valid, and B implies 1 as valid. So after applying this rule, you see that we get a succinct grammar which is precisely capturing the language captured by this context-free grammar. Okay. So you see that S imply 0 is allowed, and or you get to see B0, A0, and when you want to terminate, substitute 1 for A, and when you want to terminate, you substitute 1 for B. And similarly, when you want to terminate, this. Now let's look at what is the language accepted by this or L of G. L of G, it can accept 0, or when you substitute 1, we get 1 0, or when you substitute 1 here, it is 1 0, or when you substitute 1 1, it is 1 1 0. That is all. And there is no further recursion because S is not appearing on the right. Since S is not appearing on the right, what is generated by this must be a finite set. Substitute 1 for this, substitute 1 for this, substitute 1 for this. That is all. If you look at this grammar, on the face of it, you see that there are recursive productions. A implies BC and so on. But on simplification, we see that the language accepted by the grammar is a finite set having just 3 strings. And this is the beauty of simplification. On the face of it, you may think the language is a complicated set and it accepts an infinite set, and a careful look at the grammar, and if you systematically apply these rules, we end up seeing a simplified one, and often we will be surprised. For example, in this case, what is accepted by the grammar is just 3 strings, but if you look at this, it may appear like an infinite set. Simplification of CFG plays a vital role when we look at compiler design. More examples on the simplification and subsequently normal forms, all that we shall discuss more in detail as part of the lecture videos as well as part of tutorial sessions.